You've lived with time your entire life. You've looked at clocks, kept appointments, aged with each passing year. Time feels like the most obvious thing in the universe. It moves forward. It's the same for everyone, and it flows at a steady rate no matter where you are or how fast you're moving. Except none of that is true. Time is not what it seems. It doesn't flow at the same rate for everyone. It can stretch and compress depending on how fast you're moving or how deep you are in a gravitational field. Two people can genuinely disagree about which of two distant events happened first, and both be correct. This isn't about philosophy or wordplay. This is physics, confirmed by every atomic clock we've built, by every particle accelerator we operate, by the satellites that tell your phone where you are right now. The story of how we discovered this is the story of one of the most profound revolutions in human thought, the transition from Newton's absolute time to Einstein's relative time. It's a shift that changed not just physics, but our fundamental understanding of reality itself. For most of human history, time was considered absolute. Isaac Newton formalized this intuition in the 17th century, declaring that time flows equably without relation to anything external. In Newton's universe, time was a river flowing at the same rate everywhere, for everyone, forever. Space and time were separate entities. Space was the stage, time was the clock in the corner, and neither influenced the other. This framework wasn't just philosophy, it worked. Newtonian physics predicted planetary motions with stunning accuracy, explained terrestrial mechanics, and formed the foundation for the Industrial Revolution. When you built a bridge or launched a cannonball, Newton's laws gave you the right answer. The development of increasingly precise mechanical clocks during the Enlightenment reinforced this view. Time could be measured, synchronized across locations, divided into hours, minutes, and seconds that meant the same thing everywhere. The universe was a vast clockwork mechanism, and time was its constant heartbeat. This understanding remained unchallenged for more than 2 centuries. It took an experiment that seemed to have nothing to do with time to begin unraveling it. In 1887, Albert Michelson and Edward Morley set out to measure Earth's motion through the luminiferous ether, the hypothetical medium through which light waves were thought to propagate, analogous to how sound waves travel through air. The logic was simple. If Earth is moving through a stationary ether, then light should travel slightly faster when moving with Earth's motion and slightly slower when moving against it. Just as a swimmer moves faster downstream than upstream, they built an extraordinarily precise apparatus to measure this difference. But when they ran the experiment, they found nothing. The speed of light was identical regardless of Earth's motion. Light traveling in the direction of Earth's orbit moved at the same speed as light traveling perpendicular to it. This made no sense. If you're on a train moving at 30 meters per second and you throw a ball forward at 10 meters per second, the ball moves at 40 meters per second relative to the ground. Velocities add. That's how motion works. Except light didn't follow this rule. Light always traveled at the same speed, roughly 299,792 kilometers per second, no matter how the source or observer was moving. This result sat like an unexploded bomb in physics for nearly 2 decades. Something fundamental had to give. Either our understanding of space was wrong, or our understanding of time was wrong, or both. In 1905, Albert Einstein published a paper titled On the Electrodynamics of Moving Bodies. He was 26 years old, working as a patent clerk in Switzerland, and the paper would overturn 3 centuries of physics. Einstein's insight was to take the constancy of light speed seriously. He started with 2 postulates. The laws of physics are the same in all inertial reference frames, and the speed of light in vacuum is constant for all observers, regardless of their motion. From these simple principles, Einstein derived consequences that violated every intuition. Space and time were not separate entities. They were interwoven into a 4-dimensional fabric called spacetime. And measurements of time intervals and spatial distances depended on your motion. Time dilation was the most shocking result. A clock in motion relative to you ticks slower than an identical clock at rest. Not because of some mechanical effect, but because time itself passes at different rates for observers in relative motion. The mathematics is precise. A clock moving at a velocity v relative to you slows by a factor of the square root of minus v squared over c squared, where c is the speed of light. At everyday speeds, this factor is negligibly close to 1. But as velocities approach light speed, time dilation becomes dramatic. At 99.5% of light speed, time slows by a factor of 10. A moving clock ticks once for every 10 ticks of your stationary clock. This also meant that simultaneity was relative. Events that appear to happen at the same time for one observer can occur at different times for another observer in relative motion. There is no universal now extending across space. The implications were staggering. Time was not a universal backdrop. It was a local phenomenon, different for each observer depending on their motion through spacetime. 10 years later, Einstein extended these ideas to include gravity in his general theory of relativity. The insight was geometric. Gravity is not a force pulling objects together through space. It is a curvature of spacetime itself, caused by the presence of mass and energy. Massive objects like planets and stars warp the fabric of spacetime around them. Other objects follow the straightest possible paths, geodesics, through this curved geometry. What we experience as gravity is simply the result of moving through curved spacetime. This curvature affects time as profoundly as it affects space. Time passes at different rates depending on gravitational potential. The stronger the gravitational field, the slower time flows. On Earth, this effect is tiny but measurable. A clock at sea level ticks slightly slower than an identical clock on a mountaintop. The difference is about 1 part in 10 to the 16th per meter of elevation. Negligible in daily life, but precisely measurable with atomic clocks. Near massive compact objects, gravitational time dilation becomes extreme. Near a neutron star, time slows noticeably. Near a black hole, time dilation approaches infinity. At the event horizon of a black hole, time from the perspective of a distant observer appears to stop entirely, though this is a coordinate effect. For someone falling in, time continues normally along their own worldline. This has observable consequences. Light escaping from strong gravitational fields loses energy, shifting to longer wavelengths, gravitational redshift. The radiation from matter spiraling into black holes carries the signature of extreme time dilation. We can measure these effects with telescopes. All of this might sound like abstract theory, disconnected from everyday life. But every time you use GPS navigation, you're relying on corrections for both special and general relativity. GPS works by comparing signals from multiple satellites, each carrying atomic clocks. Your receiver calculates its position based on tiny differences in signal arrival times. This requires nanosecond precision. But those satellites are moving at about 14,000 kilometers per hour relative to Earth's surface. According to special relativity, this motion causes their clocks to lose about 7 microseconds per day compared to clocks on the ground. At the same time, the satellites orbit at about 20,000 kilometers altitude, where Earth's gravitational field is weaker. According to general relativity, this causes their clocks to gain about 45 microseconds per day compared to ground clocks. The net effect? Satellite clocks gain about 38 microseconds per day relative to Earth's surface. Without correction for this, GPS positioning would drift by about 10 kilometers per day. The system would be useless for navigation within hours. The fact that GPS works, that millions of people navigate accurately every day, is continuous, planet-scale verification of Einstein's theories. Time genuinely does flow at different rates depending on motion and gravity. The same corrections apply to deep space navigation, particle accelerator designs, high-precision timekeeping, and astronomical observations. Relativity isn't exotic physics, relevant only to extreme conditions. It's woven into the technology we use daily. So, what is time fundamentally? The physics gives us a picture quite different from Newton's absolute river. Every object follows a world line, a path through four-dimensional spacetime. The time measured by a clock moving along that world line is called proper time. This is an invariant quantity. All observers agree on the proper time between two events on a given world line, even if they disagree about coordinate time and spatial distance. Special relativity definitively eliminates any universal present moment. Events separated by space-like intervals where the spatial separation exceeds light travel time have no absolute temporal ordering. Different observers in relative motion will disagree about which event happened first, and both are correct. Our experience of a shared now is a local approximation, valid only for observers with negligible relative velocities and gravitational differences. On human scales, these effects are tiny enough to ignore, but they're always there, and in extreme conditions, they dominate. The mathematical structure of relativity suggests what physicists call a block universe. Past, present, and future all exist equally in a four-dimensional spacetime. Temporal flow, the sensation that time passes, may be an artifact of consciousness moving along a world line, not a fundamental feature of reality. Yet physics also presents a paradox. The fundamental equations are time-symmetric. They work equally well with time flowing forward or backward. But we experience several arrows of time. Entropy increases. We remember the past, not the future. The universe expands. Radiation propagates from past to future. These arrows appear to be emergent rather than fundamental. The thermodynamic arrow, entropy, increases in closed systems, likely provides the foundation for the others. And that arrow ultimately traces back to the extraordinarily low entropy state of the early universe. Why the universe began in such a special state remains one of the deepest unresolved questions in physics. There are also unresolved tensions between relativity and quantum mechanics. A complete theory reconciling Einstein's curved spacetime with quantum physics remains elusive. String theory, loop quantum gravity, and other approaches suggest time itself may be emergent from more fundamental, timeless structures. And then there's consciousness. The subjective experience of time's flow remains mysterious. Neuroscience reveals that the brain constructs a coherent present from sensory information integrated over roughly 100 to 300 millisecond windows. Memory systems create the illusion of continuous narrative from discrete neural events. But how this neural processing relates to the physical arrows of time is an active area of research spanning neuroscience and fundamental physics. Time, once considered the most obvious feature of existence, turns out to be among the most subtle and strange. Einstein's revolution replaced Newton's universal clock with a mosaic of local proper times, each valid for its own world line. Time is not absolute. It is not separate from space. It is not the same for everyone. This isn't just theory. It's measured reality, confirmed thousands of times over in laboratories and in the technology we rely on daily. GPS satellites, particle accelerators, and atomic clocks all demonstrate that time genuinely flows at different rates depending on motion and gravity. Yet fundamental mysteries persist. We don't fully understand how to reconcile relativity with quantum mechanics. We don't know why time has an arrow. We don't understand the relationship between physical time and conscious experience. These frontiers drive some of the most exciting research in contemporary physics. The exploration continues, connecting the most abstract theoretical insights with the most immediate human experiences. As you move through your day, checking time, keeping appointments, aging with each passing moment, you're navigating a dimension far stranger than Newton imagined. Time is not a river flowing around you. It's the geometry of your path through space-time, shaped by your motion and the gravitational fields you traverse. Every moment you experience is your proper time, unique to your world line. And that time, measured by the biological clocks in your cells and the atomic vibrations in your watch, is genuinely different from the time experienced by someone moving relative to you or at a different gravitational potential. We are all time travelers, moving into our own futures at rates determined by the geometry of space-time. That's not metaphor, it's the physics of the universe we inhabit.